Okay, so this is the continuation of chapter 9. Um, um, Actually, I went over this, if you remember. So we need to set up our H null and HA. H null always will have equal. Remember, null means equal, right? Um, HA will be either greater than, not equal to. I'm sorry, it's either less than, not equal to, or greater than. Okay. Actually, null does not mean equal. It means that there is nothing. So that the term null came about because of no difference. Okay, that means the parameter is exactly equal to whatever we are hypothesizing. So there is no difference. So with that in mind, is only the word null has been coined into null hypothesis. Okay, all right then. So let's go to the next slide. So here's an example where we are going to, you know, we have a problem, and then let's see how we set up the null and the alternative hypothesis. Okay. So now in the 1970s, 20 to 29-year-old men, had an average body weight of 170 pounds, and the standard deviation turned out to be 40 pounds. Okay. Now we need to test whether the average weight among men of this age group is still 170. Is it more or is it less? Now, see now whether it's more or less, which way you want to go is up to you or me to decide, the user to decide. Okay. So the idea is to compare the present population average body weight of men in this age group to 170 pounds. See, this 170 pounds was in the 1970s. Now, currently, the average body weight, which we will call to be mu, that means in 2015, okay, is that mu equal to 170? Okay, that is the question. All right. Okay, so that is our hypothesis. Now, from the hypothesis, we can make a claim. The claim could be that now, men weigh more than in the 70s, and then that means you can say on the average, the mu now is more than 170. Okay, then that would be like for HA with the greater than, okay, symbol. Let's see how this works. Okay, all right then. Um, So here, so H null is mu equal to 170. Now this is the hypothesized value. This is our hypothesized mean value. And in fact, this has a special symbol mu sub 0. We will see that very soon, okay? Now, the alternative hypothesis, now see right now, it can be tested in two ways. If we sort of have some gut feeling or some feeling that men have increased their body weight, we can say, hey, mu is more than 170. On the other hand, if you are not really sure of that, you can go with mu not equal to 170 also. So if this is the case, you will have a one-tailed or one-sided alternative hypothesis. If this is the case, you have a two-sided. Now, of course, we could have even had the other way, mu less than 170. If you think that men have lost weight compared to 1970s, okay, but maybe that the current trend may be that to think that, okay, compared to 70s, now men have increased their body weight. So that is why one of these hypotheses would be the most sensible one, okay, rather than the less than. Okay, all right. So now, of course, there are slight differences when you carry out the test of hypothesis, depending on whether we are going with greater or not equal to. Now remember, no matter which alternative hypothesis you choose, now there are three, right? Greater, not equal to, or less. Okay, no matter which one of these you choose for the alternative hypothesis, the null hypothesis is going to be always equal. So null hypothesis does not change. It's always equal to the population parameter equals some characteristic, okay, value, some specific characteristic value. Okay, all right then. Okay, so let's go to the next slide here. Okay, so now we set up our H null hypothesis and the alternative hypothesis. And remember, the second step was to come up with a test statistic. Okay, now lots of times, the test statistic will be a z. Of course, later on you will learn a few other test statistics also. Now the test statistic for that kind of a mean, there is one single mean. An appropriate one would be this. Okay, now this is the sample mean minus this is the hypothesized mean. So this is actually 170 for that example. Okay, so 170 and then standard error of the mean, which is sigma over square root n. Now sigma we found, we were given that. Okay, now so then you can calculate this z stat. Now why do we say that this is a good test statistic to test that hypothesis? Now you can kind of see, now if the sample mean is close enough to mu sub 0, which is 170 here, this z stat will be very close to 0, right? So if the z stat is close to 0, we can accept H null. Accept H null. Okay. See, if H null is true, we can expect x bar to be close to mu sub 0. That will make this near 0, right? This minus this will be a very, very, very small value. Okay. On the other hand, if the sample mean is very much away from this hypothesized mean, this z stat will be large. That means you're telling that H null, which is a null hypothesis, is not true. At least the data is telling. See, this is the data. This is our evidence. If this is much more than 170, we will have a large z stat. So what is the data telling us? Hey, don't go with this value. Do not go with 170. So in other words, roughly speaking, if this value is large, data is supporting the alternative hypothesis. If this value is near 0, data is supporting null hypothesis. Okay, so based on that logic, criterion to reject H null, if you reject H null, you are accepting HA. Remember, I said that H null and HA are rivals of each other. So if one loses, the other wins. Okay, so the criterion is to reject H null and accept HA if the z stat is away from 0. If z stat is away, if this is much larger, that means the sample mean is very much away from this. That means that the data is telling, hey, the actual mean value is not this, not 170. Okay, the actual mean value is not 170. So then that means that data sample is supporting HA. Think a little bit about this. All right. Okay. So large z values will favor HA. Near 0 z values will favor H null. All right. So let's go to the next one. So now look, let's do this example. Mu sub 0 was 170. And say we take sample of 64 men right now. I mean those who are now in that age group. Okay. And then we know that the sigma is 40. It is okay to take the same value. Sigmas do not change much. At least let's assume. Okay. Then the standard error of x bar will be sigma over square root n. Plug the numbers, you get 5. Okay. And then next slide we can calculate the z. See, the z would be 173 because that is the sample mean we found based on 64 men. Okay, so 173, this is our hypothesized mean value. This is what we are saying is the average body weight of men 170 still. Okay, so 173 minus 170 divided by 5 will give you this. Now this is actually a small value in a relative sense. So it seems as if you get the sample mean to be 173, it's telling that the average body weight of men have not changed much from 170. On the other hand, if you found a sample mean giving 185, plug 185 in here, you get a pretty nice large z value, which is 3. Okay, the z value, remember, if you sort of, we have worked with the bell curve, z value, the highest, I mean, of course, theoretically it can go on and on, but see, meaningfully, after about 3.9 or something, the probability will be near 0. Okay, so 3 is a very large z value. Okay, all right, so here's how it looks like. So now for different samples, you had, like we talked about this, n equal to 64, x bar 1, x bar for this sample 173, and then like that, if you do with the same n value 64, if you got different sample mean values, and if you did the histogram, now on the x-axis are these values, these x bar values, and then we are sort of looking to see how often would you get each one of these values, and then you create the histogram. Okay, you will get the mean of this histogram to be 170, and then n is 64 means it's large, so you'll have a bell curve, right? And the standard deviation of this will be, of course, 5, because remember, when we calculated with sigma equal to 40 and n equal to 64, we got sigma over square root n to be 5. Okay, all right then. So let's go to the next slide. Okay, so now we talked about the null hypothesis, alternative hypothesis, that was step 1. Then we talked about the z statistic, the test statistic, which is the z value or z substat, remember. The third one was p-value. I still have not explained to you what a p-value means. Okay, this is the slide which explains the p-value. Now, p-value is this probability which tells you the chance that your observed value is more than that. Okay, so if you have the observed value is 173, the probability that the mean is more than this observed value is 173. Okay, so now you can, and then look, the z value for 173 you calculate to be 0.6, remember. Now either you can use the criterion based on z or p. Now look, if p is large, that means the z is close to the actual value. Z is close to 0, which means the sample is telling the mean is actually 170. Population mean is actually 170. On the other hand, if p is very small, say this value turned out to be somewhere here, then the p is this small little tail. If p is small, then HA is probably true, because if H null is true, the p has to be much closer to, p will be very much to this side. This dark shaded area will be very much to this side, and p will keep on increasing. Okay, so now so what does it say? Let's think a little. Small p value will favor HA. Okay, so either large z value or small p value favors HA. Okay, so that is what it says here. Smaller and smaller p values will provide stronger evidence against H null. Against H null means for HA. So actually, I'll put a note in here. Small p values equivalently large z values will favor HA. Correct? See, larger the z gets, smaller the p gets. See, this darker shade will keep on decreasing. So either the smaller p values or larger z values will favor HA. Now, traditionally, before computers were not that freely available, what people would do is they will calculate the z value and then look up the standard normal tables. But nowadays with software, p-value can be calculated, and then p-value is used much more commonly than the z-value. Okay, if you are to read scientific articles, always p-values will be reported in modern articles. Okay, and on the other hand, if you are to write a scientific article, and if it is based on some data or experiment, you need to report the p-value. Okay, and then remember, smaller p-values will favor HA. Okay, now how small is small? It varies. Typical standard has been 0.05. Lots of times, lots of software, the standard or the default is 0.05. But in biostatistics, we have to be more careful because we are dealing with people's health. So for the most part, it is 0.001, and then it could even be less. There is another slide which sort of, gives you more details about, how, what this p-value should be. Okay. All right. So let's go down to the next slide. Actually, this is the same curve as what I showed in the previous slide, but this has it enlarged. You can take a good look at it, because the previous one got a little warped because I put it only to one side. So I'll give you about half a minute to look at this and then go to the next slide. Okay, so now in here z-stat, remember there was one sample which gave you z-stat to be 3.0. Now if you have z-stat to be 3.0, the p-value, see, this is z-stat 3.0, p-value is so tiny as we expected. And how do you get the p-value, by the way? You first get this left probability from the tables or from Minitab. Okay, you get this, and then 1 minus will give you the p-value that you need. Okay, so you first get this, the left side you get from the tables, and then 1 minus will give you the p-value. Okay, all right, so let's go to the next one. Now two-sided p-value. If you have HA to be two-sided, like not equal, so that means not equal, remember, then the p-value should be multiplied by 2. Okay, so that is a mathematical side of it, but let's understand why we are doing it that way. Okay, we need to, as much as possible, try to understand why we do things. Okay, now here's the significance level, especially now, like if you have p to be more than 0.1, you will say, okay, H null is most probably not true. Okay, that means HA is very much p is more than 0.1, we can say, okay, H null is true, right? If p is between 0.05 and 0.1, then there is like marginally we can accept HA. If you reject H null, we will go with HA. So if P falls in this, you will marginally accept HA. If P falls between 0.01 and 0.05, okay, so the P values keep on increasing this way. Then you have, you will say that, okay, HA is significant. Now if P is very much less than 0.01, then you will say, okay, it's highly significant. HA is highly significant. Okay. All right then. So that's how, but actually speaking, lots of times, the scientific papers that I have seen, P is like 0.001, and sometimes even after the 3 decimals, it's 0. Okay. Okay, so like P.27, that means H null is true. Okay, P.01, it means highly significant evidence against H null, which means you go with HA. Okay, so this means favors HA. Okay, all right. Okay, so let's go to the next one. Okay, now there is this alpha, which is called the significance level. Now, that is, for traditional statistics, we need that. This is actually, in fact, we will come to this later. So you can set this up, like you can set, like the user or the experimenter can say, okay, I'm going to take alpha to be 0.05. Now, what this alpha is telling is you're taking like a 5% chance of, rejecting H null and accepting HA when HA may not have been true. Okay, because see, we are making our decisions based on data. We cannot ever be 100% sure that we make the correct decision. Okay, so because of that, we have 4 different situations. We will talk about that. Okay, so always when you do a hypothesis testing, there is this alpha. There is a chance that we take. So what is the maximum chance that we are going to take? That is actually alpha. Okay, so now traditionally, if you do a hypothesis testing problem, you will calculate the p, and then you will say, okay, if p is less than the alpha that is specified, you will reject H naught. Okay, so p is smaller, so p is more to the tail area. Okay, all right then. So lots of times alpha is 0.05. That is, the standard. Okay, now here's the one sample z-test um, explanation. Okay, now the most important thing to remember is that, okay, in here the idea is to test whether the mean value is equal to something or not. Okay, so you need to have a good random sample, and then sigma, see, in the one sample z test, sigma is not calculated, it is known, it is given, like in this case. Remember, we were given that sigma was 40. Okay, and then if you have the one sample z-test, we need to have either the sample size to be more than 25, so that x bar we can say is normal, or the data x bar itself should be normal. Idea is x bar has to be normal. Okay, now if x bar is normal and if you know a sigma value, you can carry out the one sample z-test. If you do not have these conditions, we have to do something else, which we will learn. Okay, all right. Okay, so here's the setup. So we will have the null and the alternative hypothesis. It can be two-sided, left-sided, or right-sided. Then you will set up the test statistic. Then you will come up with the p-value. See, what you do is you calculate this, and then you get the cumulative probability, the left probability from the bell curve, and then you want minus that to get the p-value. And then, of course, if you are given a significance level, you compare the p that you get with the significance level. Okay, that is pretty much what it is. So let's see how that works. So here, we know that, okay, the adult intelligence scores are normal with mean 100 and standard deviation 50. Okay, that is for all adults pretty much. Say we take a sample of 9 people. So we want to see, okay, is their actual mean also is 100 or more? Are these people more intelligent than the average? Okay, so what you do is you calculate x bar. So when you take the sample mean, it turns out to be 112.8. So now, then, okay, now is this telling us that the actual mean of this subpopulation really more than 100? Because this came out to be 112. Is it really more than 100? We need to see. Okay, because see, just because you get a sample value, that does not really mean that actually the actual mean value is this. Remember, from one sample to the other, this can change. So there is that variability. Okay, so that variability should be taken into account by fitting that probability distribution, that bell curve. Okay, all right, let's go in here. So here's again we set it up. Okay, mu equals 100. Mu is the intelligent test score for that subpopulation. Okay, we are claiming that it is more than 100. Calculate the test statistic. For that, we first do the standard error. Okay, we were given that sigma is 15. Okay, and then you will have n equals 9, and then you get 2.56. Now, actually speaking, this n is not good enough for the central limit theorem. but hopefully we will assume that the individual X measurements are normal. Okay, so then now let me go back here. The Z that you got was 2.56. So then probability that Z was more than 2.56 was 0.0052. Okay. And then that you got from the left probability, and then 1 minus that, then you will get this. So 0.005 is really small. So that means, you can really say that. So if you go back to here, you can say that, okay, P small means you reject H null, you go with HA. Okay. That means it's probably true that subpopulation had a mean intelligence score of more than 100. Okay, so let's go to the next one. Yeah, I think that's pretty much. Yeah, now on the other hand, if you want to do a two-sided, if you're not sure whether it's more, you can have mu to be not equal to 100. Only difference is in the p-value. In the p-value, you will have to multiply by 2. So the p here will be 0.01, which is more, but still it is good enough. So even then, you can say that, okay, you can accept that mu is not 100. Okay. So let's see in a picture how a two-sided works. See, if the alternative hypothesis is true, that means if mean is not 100, it will be that the Z that you calculate is either very much away from 0, very large, or very small. It can go either way, because if the actual mean value is somewhere less, then you get the Z stat to be much on this side. Even then, that means mu is not 100. So when you have a two-sided test, you will have both these tails, okay, contributing towards the p-value, and both these the z value, which corresponds to those two tails, will make us accept HA. Okay, either on the positive side or on the negative side. Okay, that's the only difference between a one-sided test and a two-sided test. The p-value doubles, and then sort of like the rejection region for H null will be on both sides. Okay. 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 Now let me also talk about the power and the sample size. Now, see, we do not really need power and sample size, but we need to understand this table. Remember, I told you that data will not be, telling us the truth, the perfect truth all the time. In other words, the decision that we make, we cannot be 100% sure. Okay. Now, we will make two decisions based on data. Either you will keep H null, retain H null, or you will reject it. But see, that is based on data. Data cannot be 100% accurate. So the truth could be sometimes different from our decision. So in the truth, H null could either be true or false. So we have four situations that we may encounter. When H null is true, the data will tell us to retain H null. Great, good decision. When H null is false, still the data sometimes, at least few times, will tell us to retain H null. Not a good decision, and that error, that type of error is called type 2. Okay. When H null is true, the data will tell, don't accept it, go with HA. Another error, type 1. See, these two errors are different. Here you are rejecting H null when it is true, and here you are retaining H null when it is false. So both are errors, but the description of the two errors are different. Okay. And then finally, the data will reject H null when H null is false. Oh, that's great. Okay. So these two situations, we would like to be in these two situations rather than these two, but we cannot avoid these. there will be at least a very small chance that one of these can happen. So now if you increase the sample size, we can decrease the chances of both these two errors happening, okay? But we cannot ever make them completely zero. Now type 1 error is the error of rejecting H null when H null is true. Now the probability of that, see, the probability of this type 1 error is this alpha. Remember we talked about the significance level. Now that is alpha. So that is why I said, okay, alpha is the risk you take in rejecting H null, when it is true. Okay, so that's an error, and so we are taking alpha percent chance. Then also this type 2 error probability is called beta. Okay, now beta we cannot set up because, see, this depends on the actual value of the mean, which we do not know, right? If HA is true, that means mu is more than 170 in that example. But we do not know, is it 180, is it 190, we do not know. So the actual mu value determines this beta, or at least that is one factor which determines beta. So because of that, we never can figure out the beta. Luckily, we can figure out alpha. So as an experimenter, you can say, I'm willing to take a 5% chance of rejecting H null even when it is true. We do not know when it is true, right? So, okay, so this table is important, okay? We need to learn how to write the type 1 error and the type 2 error for different word problems. So we will practice with that, okay? Okay, so now actually, yeah, I'm sort of elaborating that table over here. So this is how it looks like. Um, either we will have either of these two decisions: reject H null or retain H null. Oops, this should be H null. Okay. Now, depending on the decision, only you will make a certain error. Type 1 error happens if you reject H null. Okay. And then type 2 happens if you retain H null. Okay. And then, okay, this is not the decision, it's a description. Oops. So right in this column, I have described the error. Type 1 error is to reject H null when it is true, and type 2 error is to retain H null when it is false, right? Yeah, that's also error. Okay. So now look, in our problem we rejected H null. Are we 100% sure? No. Okay. Now we concluded that the mean weight of 20 to 29-year-olds is more than 170. But there is this type 1 error involved in here. We are not sure 100%. There's a small chance that we may have made a mistake. We have accepted that the mean body weight of men this year is more than 170 when actually it is not. Okay, so now this can be serious to certain people, right? If people are concerned about body weight going up and it is a health risk, and if type 1 error happened here, that means that worry is in vain. Okay, it's, if type 1 error has happened, men's weights have not increased, but people will be worrying about it, saying that, hey, now men are much heavier than they used to be. Okay. Okay, so actually this is pretty much what I talked about. Now power is not included, so there are 2 or 3 more slides that talks about power, but we don't need that. So these last few slides, you don't have to be concerned for this class, okay? But for completeness sake, I kept them. If you do a more advanced stat class, I'm sure you will come across it. Okay, so that's the end. Oh, this took 35 minutes. I hope I can, download it.